In this video, we're going to look at a few different questions about the waves topic. So stationary waves, progressive waves, optics, diffraction, and everything in between. So in this question we've got from 2022, we've got light going from air into another substance with a refractive index 1.62, then going into substance B, which has a different refractive index. And we're asked to explain how the path of the ray, so this thing here, shows that the refractive index of A is greater than the refractive index of B. And even though it's a 1 mark question, it is an explain question, so we have got to be careful with getting the right terms in. So anything to do with refraction, we're going to think about Snell's law. So Snell's law says that if I multiply the refractive index by the sine of the initial angle, that equals the refractive index of material 2 times by the sine of angle 2. So if I was to do a quick rearrangement of this, I would say something like, if I divide the two refractive indexes, so 1 over 2, that's going to equal, if I rearrange this, sine of theta 2 over 1. So let's look at the two angles we've got. We've got this initial angle, so that's theta 1, this angle 2, theta 2. We can see that 2 is bigger than 1, so that's going to mean, there should be a 1 on the bottom there, so therefore sine theta 2 over theta 1 is greater than 1. So therefore, it tells us that actually this fraction has to be less than 1. So we could say, so therefore, and 1 refractive index A is less than in 2 refractive index B. Next question, and we've got to show the angle of refraction in ray B is about 60 degrees. So we're talking about this angle here, which you just sketched on. So we need to do a little bit of calculations to work this out. Now, if you look carefully, we don't actually have either theta 1 or theta 2 in our answer. So we're going to have to use a little bit of kind of problem solving to work out theta 1 first. So how do we do that? Well, if I just sketch out the shape we've got here, we can kind of clearly see we can work out what this angle is here. If I know that these two angles, these angles all on a straight line are going to equal 180, I can tell that this one, because it's normal, is going to equal 90. So therefore, what we can figure out is then these two here have to equal 90. So therefore, my angle 1 is equal to 90 minus, and this angle is going to be the same as this one down here due to similar angles. So this one's going to be 43, this one's also going to be 43, so therefore 90 minus 43 equals 47. Once we've got that, we're just going to get back to using Snell's law, and let's plug in some numbers and see what we get. So our refractive index 1 is 1.62, the angle we've just worked out is 47, and refractive index of material B is 1.35, and we don't know what the angle of refraction is, so that's what we're trying to find out. So sine minus 1, we've got 1.62 times by sine 47 divided by 1.35, and if you stick that into your calculator, you should find that equals 61.4, which rounds to 60. We're going to write down our full answer. Next question looks like the easiest one. It's just a drawing question, but it's worth 3 marks. It says, draw onto the figure the path of the ray immediately after it reaches P to justify your answer with calculations. So what it means is here, what is going to happen to that ray? So there's two options really. Either total internal reflection could happen, or it could just refract through. Now, to determine which one of those is going to happen, we need to know what the critical angle is. Okay, because if it's bigger than the critical angle, total internal reflection will happen. If it's smaller than it, refraction will happen. So how do we work out the critical angle? So using Snell's law, a kind of short derivation of that says that if I have sine of the critical angle, it equals to the ratio of the refractive indexes. Now this time we're just talking about it leaving the glass block and going into air. So actually it makes our life a bit easier because the refractive index of air is obviously 1. So therefore it becomes 1 over refractive index material B is 1.35. So let's work this out first. Let's stick our numbers into a calculator and see what that gives. So therefore C is equal to 48 degrees. Okay, so that's our critical angle. And then we've got to figure out, well, what is this angle here? What is the angle of incidence it comes in at? Because we're not necessarily given that. We've got to figure out, is this bigger or smaller than critical angle, or how do we know what it is? So let's have a look at this triangle here, this kind of slanted triangle here. Let's figure out angles we know. So this one is obviously going to be 180 minus 43, which is going to equal 137. Next we've got this angle up here. Now we know what theta 2 is, so therefore if both those angles make 90, 90 minus theta 2, which you just worked out, is going to equal this angle here. I'm going to use my other raw value, so that's going to be 90 minus 61.4. 4, and that leaves us then this angle here. So we can work out this angle by saying, I'm going to do it down here, just good practice to do it on your equation sheet. So 180 minus 137 minus 38.6. So this 90 minus my angle from earlier 61.4 equals 28.6. So therefore, now if I find this angle out, I need to do 180. So the angle in a triangle minus 137 minus 28.6. So that all comes to, if you work it out, 14.4 degrees. So therefore I can say the angle down here, show you workings as well, make sure you don't lose marks that way, minus 28.6 equals 14.4. Now that's not my final angle, I've got to figure out this bit here, but that's straightforward because it's just 90 minus 14.4. So therefore, so I'm going to write down the angle of incidence here equals 90 minus 14.4, which is equal to 75.6. Okay, around to 76 on the mark scheme. Now the last bit is then to figure out, well, is this going to be greater than the critical angle or not? Hopefully it's obvious this definitely is bigger, but you have got to say it, and therefore you can say 75.6 is greater than critical angle, so it reflects, CO2 internal reflection occurs. And we have got to draw it on, so let's get ourselves our ruler, and we're looking for the angle of incidence to be roughly the same as the angle of reflection, so it should be something like this to get our full marks for that question. Okay, next question we've got is a bit more about waves in general and about diffraction. So let's have a look. So as a student investigates the interference of sound waves using two loudspeakers connected to a signal generator, each loudspeaker acts as a point source. Now, even though it's sound waves, this basically comes into the optics topic when you cover diffraction. So classic exam questions using something you know to kind of ask you about something you don't know. Tells you about point O, we'll come to that later. First question is explain why the two loudspeakers are coherent sources of sound waves. So you need to know what that word coherent means. So for the first mark, we've got to say coherent means the two sounds here have the same frequency. You could say wavelength, the same frequency is fine. And they have what's called a constant phase difference. So note, they're not necessarily in phase, but they'll have a constant phase difference because they've got the same frequency. Two waves, if they are slightly out of phase, will be out of phase by the same amount each time. Now, how do we know the two loudspeakers are coherent sources of sound waves? Well, if you look carefully, they're both connected to the same signal generator, okay? So you could say something like this is because they are connected to the same signal generator. Okay, next question is asking the student faces the two loudspeakers, they're equal distances, then they move from point A to point B, so basically up in this direction. Then it says as the head moves from A to B, the amplitude he hears decreases, then increases, and then decreases again as he moves beyond B. Explain why the variation in amplitude occurs as he moves from A to B. Now, I said earlier, this is very similar to when you would have covered light diffraction, or diffraction of light from a two-slit source. So with light diffraction, it would be bright and dark fringes, and this time it's just loud and quiet sounds. It is basically exactly the same answer, you just got to talk about sound waves instead. Okay, so how would we answer that question? This is a kind of classic 3-mark answer for these kinds of questions. So how do we get the bright and the, sorry, not bright, how do we get the loud and quiet sounds? Well, it's to do with superposition, okay? So the sound from the two speakers superposes, basically, or a superposition occurs. And then more specifically, so first mark for that one, more specifically, well, what does that happens at the loud bits, what happens at the quiet bits, okay? So then you say at A, so use the diagram. So at A, there is, you could say it's constructive interference, but really what we're looking for here is that they are in phase with each other, okay? So the waves are in phase. You could talk about the path difference here, but they're in phase, so you could say constructive interference. If you're not sure about that, that means the wave meeting exactly peak meets peak, so therefore the amplitude is increased. So therefore at A, that's what's happening. As you move a bit further away, so the idea is that by the time you get to B, it says is decreased. So therefore we could talk about at B, what's happening, the waves are in antiphase. Okay, so waves are in antiphase. Okay, so at towards B, so between A and B, what we say is that the waves become in anti-phase, or you could just say they're out of phase. Okay, so there is a phase difference, so that's why it starts to get quieter. Then you can say at B, you could basically repeat the same answer for A. We're not going to here because that's enough for a mark, but the waves become in phase again. That's why the amplitude starts to increase again. So that's our 3 marks for that bit of the question. Okay, now for this next part of the question, this is a particularly sort of tricky part of the question, to try and find out what that thing is asking you to work out. So we've got some data. We've got the separation between the speakers. We've got distance OA, A to B, and it's asking us to show the path difference for the sound between the two loudspeakers at point B is 0.1. Okay, so it's a show question, so we know what the answer should be, but we've got to go back to the diagram and start labeling on. What we're going to do is actually just label it on this one here, because it's basically the same diagram, ignoring C for now. So what do we have given to us? It tells us P to Q, the distance between the speakers, is 0.3 meters. It tells us O to A, this bit here, 2.25 meters. And it tells us A to B, so this bit here is 0.95. So what I've got to figure out is, well, it's asking us between A and B. We know that A was a maximum, and B is also a maximum. Okay, so essentially what we're looking for is the overall kind of path difference, which we should find to be about 1 wavelength, but we've got to use a bit of trigonometry because we do not know anything about the actual paths themselves. So let's draw them in first, then that'll help us figure out what triangles we might need to draw. So it's going to look quite messy. You wouldn't necessarily need to draw all this out in the exam to get marks, but it's worth doing just to help explanations. Okay, so we need to work out essentially the difference between these lines. Okay, so that's going to be our path difference. So how do we do that? Well, if we were to kind of sketch out these two triangles, so I'm just going to draw them to the side here to make it a bit easier to see. So this is P to B. Now we do know the length of this one because that's given to us already. That's 2.25 meters. Now this distance here, even though it's not given to you, you can work out. So for this triangle then, we know that it's 0.95 in total between A and B, and we know that this distance here is half of 0.3. So to work out the distance between our point A and B then, we do 0.95, which is the total, minus half of 0.3, so that's 0.15. So then let's work this out on our equation over here then. So we've got Pythagoras PB to this distance here, the hypotenuse is 2.25 squared plus whatever this is squared. So that's going to be plus, I'm going to leave it all in the bracket for now, minus 0.15 all squared. So that's all in the square root still. If you chuck that into your calculator, it should equal around about 2.39 meters. Next, once we refer to how to do that one, QB becomes a fair bit easier because if I was to sketch out that triangle, this time I could do it in red, we've got a similar sort of idea in that we know what the horizontal length is, because that's 2.25. This length is what we're trying to find. Now this length is the distance between A and B, so 0.95 plus, this time we know it's a bit extra because the distance between Q and O is going to be again half of 0.13, so that becomes 0.15. So this time if I'm trying to figure out what instead of PB is, instead this time I'm going to work out what QB is, and that is big square root, again 2.25 plus, and this time I've got those two values added together, 0.95 plus 0.15. Okay, if you stick that into your calculator, you should get a slightly higher answer of 2.50. Now, path difference is literally just the difference in paths. So that's taken slightly longer, that's taken slightly shorter. So therefore, what are we going to work out to do? We're going to work out the difference between them. So therefore, path difference is 2.50 minus 2.39. Which equals 0.11. And it's very hard to kind of fudge an answer for this question because obviously we know it's 0.1, but they are looking for this value, 0.11. For the next question, I'm going to try and work out the speed of sound. So frequency times wavelength. Frequency they give to you 2960. Now the wavelength, I did mention this earlier, the path difference, because it's the first maximum to maximum, that is only going to be equal to 1 wavelength or lambda. Okay, so therefore we can just use our value from up here. You might have got something slightly different there. Error code forward you get given to you. So therefore for my value of 0.11, it's going to equal this. So 2325.6. I'm going to leave it to 3 sig figs because it in the question is 3 sig figs as well. And little top tip here as well, if you get a show question, almost always following that, or a couple of questions following that, you'll be asked to use that value. So it's definitely worth bearing in mind if you're not sure how to do a question after that. How do I go about doing it? Well, you might need to use the value you've been asked to show already. Okay, next question. We've got a student moving the head to point C. Now I've messed up this diagram slightly because I've scribbled all over it, but the idea is that it says the emitted frequency has gradually decreased, and says discuss the effect that the decrease in frequency has on the amplitude of the sound heard. So the frequency's gone down. If there's someone standing at C, how is what they're going to hear be slightly different? Okay, so let's kind of start from the basics. What do we know? Well, we're going to know that the path difference is probably going to change because we know frequency is related to wavelength. So we do get a mark here for saying, well, if frequency is going to be decreased, that means wavelength has increased because they're inversely proportional for constant speed. So the idea is then, if I was someone at C, the path difference before was 0.11. If the wavelength going up, that means path difference is increasing as well. So therefore, if it's increasing slightly, initially you had to be this distance to this distance. If it is increasing, it means that actually that distance would have gone slightly higher. There's going to be kind of path difference at C is going to be closer to one wavelength, or the separation of the maximum is going to increase. So if that's happening, if they're more likely to be at a maximum now, therefore essentially the amplitude will increase or get louder. So amplitude will increase as more waves are in phase, or more likely to be in phase. And there's our 3 marks for that question. Right, to finish on today, we've got a question all about stationary waves. So we've got a vibration generator in equipment that should be familiar with you. You would have done this at a practical at some point. And you've got some kind of tape affixed to 2 markers, P and Q, that are 0.55 meters apart from each other. And it says the spring is made to vibrate at the second harmonic. Compare the motion, so how are they moving with P with that of Q. So the bit in the question they don't draw out for you is what the second harmonic looks like. So we should know the second harmonic means 2 loops. So therefore the wave looks a bit like this. So I've got marker P is around about, so the whole thing's like that. So marker P is around about here. And got marker Q on my diagram is going to be around about here. Okay, so don't tell us the whole thing. You can sketch on if you want to, but the idea is you don't need to know exactly how far apart they are for this question. All we need to know is that in a stationary wave, particles that have a node between them oscillate in antiphase. So as one's going up, the other's going down, and vice versa. Okay, because the opposite kind of all the particles in this part of the string will be in antiphase to this part of the string. So we've got to say something like, so particles are in antiphase, or the tapes, are in antiphase to each other, or pi radians out if you wanted to be doubly sure. And the idea is then, well, what's happening in terms of their motion? They are in antiphase. What does that actually mean? There's a couple of things you could say here. You could say they have similar amplitudes because they're both kind of equidistant from the nodes at the end. You could say they have the same frequency, which is probably what I'd go with, or time period of oscillation. We could say that same amplitude. You could say about same speed as well. I'm about to say those are the obvious ones. So any 2 from those 3 would be what you're looking for. But I'd say the top 2 are probably the most key ones there. Right, next question. We've got the similar idea. We've got a wave drawn on with a higher harmonic this time. So we aren't told what it is, but there's a higher harmonic. And it's given us the frequency, and we're asked to work out the wave speed. So we know wave speed equals frequency times wavelength. And so how do we use that in our answer? Well, with frequency we're given to us, which is pretty handy. So that's 250 hertz. And then we've got to work out, well, what is the wavelength? So it's 0.55 is given to us up here. So we can then figure out, so working out the wavelength. The reason this question is a little bit tricky is because it kind of looks like the wavelength is going to be this whole thing. However, it's not, because it's a stationary wave. At another instant in time, it's going to look like this. So how many harmonics are there? Well, there's kind of 3 antinodes, 4 antinodes, 5 antinodes. So the idea is the one wavelength is going to equal basically the distance between just one peak to one peak, essentially. Okay, so up, down, or down, up, down. Slightly confusing diagram like that. So basically it's going to be, if you look, there's kind of half of the 0.55 is going to be equal to one wavelength. So therefore, if we chuck our numbers in, we're going to get a calculation with speed equal to 68.75 for us. We can round it because it should be 2 sig figs with our 2 sig figs given in our question. Okay, next one, we're going to look at the instantaneous position of the string. So this can be explained by superposition of two waves. Then it gives you the instantaneous position between P and Q. Describe the properties that the waves must have to form the shape shown. So even though I think the way they phrase that question is a tiny bit like misleading, but what it's basically asking us, the shape shown, well, it's a stationary wave, and they even tell us that there's the superposition of waves. So essentially, 3 marks. Describe what makes a stationary wave. So we're going to say, so two waves traveling at the same speed, and they're going opposite directions, and they have the same wavelength, or same frequency, same amplitudes would work as well. But that's your 3 marks there. It's not more complex than that. The idea is they're just trying to get you to that information out of you by phrasing it in a slightly different question. Okay, so next we've got some more diagrams. Shows the position of the two waves between P and Q a short time later. So we've got this bit. We can see the peak matched up with a trough here and trough matched up with a peak here. It says draw on figure 12 the appearance of the string at this instant. So it says this time we're drawing the appearance of the string. So the string is P and Q together, so we've got to do a bit of superposition. So peak matches trough, trough matches peak. That means that the whole wave is going to be a flat line. So it's going to be kind of destructive interference at each point. Then it says to annotate on with positions of any antinodes on your drawing. Okay, so where are the antinodes? So basically, if you look carefully, we've got antinode, this one here. Make sure you're matching it properly. We've got this one here. So about this far along, we've got the, where are we? This point here. Sorry, I've started those in the wrong spot. So we've got an A here, we've got an A at the other end, and we've got one directly in the middle, so ignore this one, and we've got 3 halfway along basically. Okay, so how do we know that? We've got to look back at the previous question and figure out, well, this is the instantaneous appearance of the wave. We've got antinode, 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 so 5 in total for that part of the question. Right, to finish off, we are going to give us a new situation. So the frequency is reduced, the first harmonic is observed, says the string is replaced with one with 9 times the mass per unit length, everything else is constant, and including the tension, deduce the harmonic observed. So what are we going to kind of try and figure out? Well, the equation we're going to use is this one here. So F equals 1 over 2L, big square root, time tension divided by mass per unit length. And our job is to figure out, well, if this has got 9 times the mass per unit length, what is going to happen to the frequency, the fundamental frequency? So if everything else is constant, the relationship between F and mass per unit length is one of the kind of inverse inside a square root. So it looks like that. So if I put a 9 here, what that means is that because it's in a square root, F is going to have to go, if that's increased by a factor of 9, F is going to have to go down because it's 1 over. Because it's in a square root, it's only going to go down by a third. Okay, so because it's the square root of 9 is 3, it's gone down by a third. So we'd say F has reduced by a third or gone down by a factor of 3. So therefore, what do we what can we use to work out the harmonic? So if this is the frequency of the first harmonic, so that's the fundamental frequency of the first harmonic, which harmonic is then observed? Well, let's just put numbers in. Let's say that's 10 hertz, then 20 hertz, 30 hertz would be the original frequency, and that's going to mean it's going to be the third harmonic. So therefore, we could say something like the third harmonic is observed if we change that mass per unit length. So we're going to have something like something like this, 3 loops, a bit neater than that. God, that's not very at all. But anyway, that's enough just to say that as long as your working's clear enough, that will be fine for your 3 marks for that question.